Okay, so let's start part 1 of circle geometry. Okay, now I'm going to show you everything that's required for this unit. This is not broken down. We're not going to do all of it today. But what the curriculum says you need to know for this is solve problems using circles, including the perpendicular from the center to a chord, which bisects the chord. The measure of a central angle equal to twice the measure of the inscribed angle subtended by the same arc. The inscribed angles subtended by the same arc are congruent, and a tangent to a circle is perpendicular to the radius. At this point I'm going to stop reading because most of what I'm going to cover in part 2 will be the remainder of what's going on there. So here's some new words we're going to have to pick up. What the heck is a central angle, an inscribed angle? What does the word subtended mean? What does the word arc mean? What does the word chord mean? So these are some of the words that we're going to pick up now in my explanation. Okay, first a bit of a review for you guys. So the terminology. Obviously a circle is something we all know, but the way it's defined in math is a curved line with every single point on this line equally distant from a center point. That's what makes it a circle, is that every point along the line is the same distance from the center, okay? And that the line is curved and not straight, okay? A radius line is the distance. It's the straight line you draw from the center of the circle to the edge of the circle. You guys, a lot of you said you knew that already. That's great. Usually in math, they write radius with the letter R to represent radius. A diameter is, instead of going to the center, it goes straight across the circle, but a diameter has to pass through the center as it goes there. So as you're traveling from one end of the circle to the other, if you go through the center of the circle, that's called the diameter. Now the diameter and the radius are related. The diameter is basically two radius, or two radii, combined together. So you can even express that in formulas. The diameter is 2 times the radius, or the radius is half of the diameter. So far, so good. Pretty simple to think of, and I hope for a lot of you that's review. The circumference, which is often expressed with the capital letter C, is the whole distance around. So if you were going to walk around the outside of a circle, the number of steps you'd take would be your circumference, okay? Now, here's where this weird value comes. If you divide the circumference by its diameter, so that circumference divided by diameter, you get this value pi, 3.145, etc., etc. We usually, because that number is infinite, it never ends, we usually, instead of writing the number, often express it in math with the Greek symbol pi, okay? But that gives us equations as well. Equations that in reality you don't have to work with too much in this unit. Things like pi equals circumference over diameter, or pi equals circumference divided by 2 times the radius, which is the same as the diameter, okay? And from there you can shuffle the formula around. You can use your algebra to shuffle it around and solve for things that might be missing, okay? And again, I think a lot of you have already done that in previous units working with circles. But that's the basics, right? Diameter, radius, circumference. And the value pi is the basics of working with a circle. Now, a chord is defined as any straight line drawn from one point in a circle to another point in a circle. Now, that might be a little different than a diameter because, as you can see, that chord does not travel through the center. If it does travel through the center, it's still a chord, but now it's also a diameter. So diameter and chord could be the same thing. But a chord does not have to pass through the center. It's like you're slicing the circle in a different way. Okay? All right. So now that we have all those terms down, let's start looking at angles within the circle. Here's the new content that this unit tries to focus on. Okay. Here's the first one. If you have a circle that have 2 radii, 2 radius lines. Now remember, a radius line goes from the center to the edge. So it has to go from the center to the edge, and we have 2 of them. If you have 2 of those radii, they form what's called a central angle. So right there you can see that's a central angle. Okay? Now, I want to challenge you a little bit right now. See if any of you can kind of pick up on this. Let me just jump ahead to a blank one. Let's make things a little bit harder. Okay, now don't criticize my circle drawing skills here. But let's say we had a circle and a center, okay? Now I could draw a radius line, but instead I'm going to draw a diameter line. So it goes through the center from one end to the other. Is there a central angle formed? What do you think, Simon? You're 100% correct. There is an angle right here. This is a radius line. This is a radius line. The angle it forms would be 180 degrees. You're right. That's something that I often see, by the way, on exams. The students kind of misinterpret that. If you see a diameter line, it's still forming a central angle. Now, I could have drawn two different radius lines. I could have drawn one here, and that, I don't know what that angle is, but it's a central angle. A central angle is defined as two radii coming off the center, forming an angle. So a diameter is still two radii. So that still applies, okay? And you actually knew what the angle itself was, which is even better, okay? So don't be confused by that. That's what a central angle is. Now, if we have two chords, which means they don't pass through the center, and they have a common end point, which would be somewhere along the circle, they form what's called an inscribed angle. Here's an example. So I have a point creating a chord, and this point creating another chord. But notice they share the same point. So that point is shared by this chord and that chord. That forms an inscribed angle, okay? That's the difference. This is what's called a central angle. This is what's called an inscribed angle. Okay. Now, an arc is defined as a portion of a circle. That's pretty simple, okay? So it's often identified by points. The way you can describe an arc is to say, well, there's an arc between A and B. So that's what it's talking about, this arc here that's going between A and B. It's a portion of the circle. If you have an arc that's half of the circle, it's called a semicircle, right? A semicircle is an arc that's half of the circle, okay? The other term, and you're only ever going to run across this term in geometry, the term subtended means it's an arc created by an inscribed or a central angle, okay? In a minute, you'll kind of get more context to what I mean by that. Okay, so here's the diagram I'm going to show you, okay? Here's a radius line, BC, okay? So here's the way you can describe it. It's a line that goes from B to C. There you go. It's a radius. So it goes from the center to the edge. Here's the radius line, AB. What do they form? A central angle. That's right. In there is a central angle because two radii form a central angle. We could describe that angle as angle ABC. See how that works? Does the order of the letters matter? Could I have called it ACB? Could I have called it CBA? Could I call it CAB, cab, or back? What do you think? Simon? It would get confusing. So what's the best way to use it? Not necessarily alphabetically. It's the center letter that matters. Why is B in the center of those three letters? Why is it the second letter I'm describing, Simon? That's right. B is where the angle takes place, right? So it goes A, B, C. I could have called it C, B, A, and it would be just as valid. But that middle letter matters. Because you're going to see questions like that, where it says angle ABC, because you wouldn't want to screw it up. You wouldn't want to think that the angle is somewhere else, right? It's at that center letter, okay? So that's what we know. Now, that also forms an arc. An arc between A and C is formed by that central angle. So that's what we know about this circle. Now, in the same circle, so we'll assume that that stuff's still on there, we also have a chord called AD. Now remember, a chord doesn't have to pass through the center, which it doesn't. We have another chord, DC, so it goes from D to C. Now, well, here's what we know about this chord. They share an endpoint. So what does that form, those two chords? An inscribed angle, that's right. That forms an inscribed angle right here. not a central angle, because central angles only involve radii. But it also forms an arc, too, right? It forms, in fact, the same arc, or it subtends the same arc, which means both of those chords and radii share the same arc. Okay? That's important, because what that means is what I'm going to go over next. Okay? But that's what I mean by the terminology. Here's we have a central angle. Here we have an inscribed angle. Both of those angles, they're not the same angle, but both of those angles are shared by that arc, or they subtend the same arc. Okay? Because here's where it gets tricky now. This leads to two circle properties. One, inscribed angles subtended by the same arc are congruent. Two, the measure of a central angle is equal to twice the measure of an inscribed angle, subtended by the same arc. Okay, we're going to do a problem with that in a minute. But this will be in your notes so that you know what these properties are, in your textbook as well, so you have a feeling for what's going on there. So here you can see I have ADC forming an inscribed angle. I also have AEC forming an inscribed angle. But both of those share the same arc. So according to property 1, whatever that little angle is there, it's the same as that little angle right there. They're congruent. As well, I have ABC, and B is the center. So that forms right there a central angle. Here's what else I know. Whatever these two angles are, we know they're equal. They're half of what that angle is. So that angle looks like almost 90 degrees. Let's say it is 90 degrees. So that would tell me that these two little guys are both 45 degrees. Okay? You can actually use the properties of a circle to figure out angles. This is important in some jobs. For example, construction, huge part of that. Okay? Okay. Okay. So let's talk about how that relates now to something called bisectors. Okay? What a bisector line is, it's a line that crosses another line to cut it directly in half. So if this line, this red line, goes across the yellow line, it's going to cut the yellow line into two equal parts. Okay? It's like if you had a carrot and you want to cut it directly down the middle, you're bisecting that carrot so that you have two equal halves. Okay? A perpendicular bisector is a line that cuts it in half, but cuts it in half at a 90-degree angle. So that you can see happening right there. So what we're happening right there is we have what's called a perpendicular bisector. Okay, how this relates is if you do that with a chord. So if you have a perpendicular bisector to a chord in a circle, okay, the chord must pass through the center. That's the only way that would work. For any chord you draw, okay, let me try and draw this for you just so you get a feel for this. Okay, so I'll just draw another circle here real quick. Okay. Okay, so let me just draw a chord, any chord. So I'll just go, okay, there's a chord. Okay? If I was going to draw a line in blue that cuts that red line in half exactly, it would be somewhere around here, right? Somewhere around there it would cut it in half. Agreed? Now, the line that's going to cut it in half must be at a 90-degree angle. Correct? Well, no matter what that line is then, I know it must somehow pass through the center. And that will apply to any chord I draw, right? So I could draw a chord like this. And then if I drew a bisector right in the middle, and it was at a 90 degree, it would pass through the center. That's the property of a perpendicular bisector as it applies to a chord.
Can bisectors not pass through the center?
They can. Good question. Let me back up. Okay? So let's draw a bisector for this line. So that's the middle spot. Couldn't I bisect it like this?
Oh, yeah.
Is it perpendicular? No. In order to make it perpendicular, I'd have to take that line and turn it to a 90-degree angle. And then guess what? At that point, it would go through the center. So that's a good question. You can have bisectors that aren't perpendicular, but then they won't go through the center. But the second it's perpendicular, you know it goes through the center. Okay? So the shortest path between the center of a circle and a chord is the perpendicular bisector. So again, this would be applicable to careers like mapping and stuff like that, and designing and carpentry and things like that, where you want to figure out these types of things. This knowledge of circle geometry, very helpful. Okay, let's run through a couple examples. These are sample questions. Here's a circle. We know that the angle ADB, right there, is 35 degrees. What's the central angle? ACB. Good question. Now I put this same problem, oops, up here. Okay? So here's what we know. We know this angle right here, 74. What we're looking for is what's this angle right here. That's what we don't know. So we have no idea. But we do know a few things. We know that both this angle here and that angle share the same arc. See that? They subtend the same arc. So what does that tell us? Well, first of all, is this angle here an inscribed angle or a central angle? Right, so we'll put an I there. That's an inscribed angle. Is this angle a central angle or an inscribed angle? Right, and we know that because central angles involve radii coming from the center. Ah, perfect. We know that inscribed angles involve chords that share a common point. Perfect. What we also know is a relationship between them. If they share the same arc, which they do, then we know that the central angle is double the inscribed angle. Oh, so if it's double, it's just 74 times 2, which equals what?
148
degrees. Okay. Oh, did I get that right? 8. Oh, I'm sorry, I went backwards. I did it the wrong way. Hang on. I wrote this wrong. 74 isn't that one. 74 is that one. This one is 74. This one we don't know. Oh, but now how would we solve that? It's half of it. It's 74 divided by 2, which is?
37.
37 degrees. You got it. Okay. Let's try another one. Okay, so now here's what we have. Lots of lines on this circle. But here's what we know. Angle ACB. So that's this one. ACB. What kind of angle is that, ACB? Use a word to describe it. It's not, no. What kind of angle is ACB? Not inscribed. Central angle. Good guess, but wrong guess. What we know about it, it's 74 degrees. So there's 74. Now, what it's asking for is what's this one and what's this one? We don't know what they are. But here's what we know. They share the same arc. This is an inscribed angle, and this is an inscribed angle. So let's just deal with this one. Let's give them names. What do you want to call this one? No, let's give it a good name. That's angle ADB. What's the other one called? Angle EB. Right, that center letter matters. We don't know what they are. But we can take any of them. What do we know about this one? It's half of that, which we just figured out, which is what? 37 degrees. But we also know one other property of this. Two inscribed angles that share the same arc are the same. So this one is also 37 degrees. Okay? As a matter of fact, I could draw one right here. I could draw my own chord. From there to there, from there to there. What's this angle?
45?
Nope. 37. It has to be. Because it shares the same arc as the central angle, and it's half of the central angle. I could draw any inscribed angle on there, and it would be 37. Okay. Let's try this one. Here's a circle with C as the center, And AB, so this line, A to B, is a diameter line. We know that there's a chord, A to D, which is 12 centimeters long. We know there's another chord, B to D, which is 5 centimeters long. Right there. What's the measure of angle ADB? So what I'm asking for is what's this angle right here? Now, for those of you who are thinking like the stuff that you learned in grade 8 about Pythagorean theorem and stuff like that, that's not going to apply here. But if you think back to the beginning of this presentation, I talked about arcs. Is A, C, and B form an arc? How would you describe this arc? What's another way to describe this arc? A semicircle, yeah, that's a semicircle right there. Go away. Oh, now it's just being a pain. Right, that's a semicircle. Does angle ADB share that arc? So is this a central angle? Right there. Is that what is that? It's an I1. Yeah, it's an inscribed angle. What do we know about inscribed angles? A central angle. Is AC it's 90 degrees. That's right. Because it's exactly half of 180, which is 90. Okay? So you can see a lot of these questions require no work other than knowing your circle stuff. Look how much calculations I had to do here. Nothing. Now, that's not going to apply in the next one, but let's see. All right, so here's what we got with this one. Here's what we know. We know that we have a radius, C to D, and it bisects this chord, AB. It bisects it, which means that this side of the chord is equal to this side of the chord. It cut it in half. Exactly in half. And notice it comes off of the center. What that means is the only way that would work is if this is a perpendicular bisector. So now we know what that angle is right there. It's 90. Now, what else do we know? We know that the length of distance from A to B, this whole distance, is 8 centimeters. Do we know what the two little halves are? What are they?
4.
How do you know that? You're right. But how do we know it's half? No, but how do we know that it's cutting it in half? Because it says it does as a bisector. As a bisector, we know it has to cut it in half. So that's 4, that's 4. What else do we know? The diameter of a circle, so the distance across, if it was drawn, it's not drawn, is 10 centimeters. So if we know the diameter, what's the radius? That's right. Which is what it tells us AC is. It tells us that AC is a radius. So this is 5 centimeters. So really we have this little triangle now. A right angle triangle where this is 5, this is 4, and what it's asking for is the distance between C and E. It's asking for this. Have you ever seen a problem like that before?
Don't just use Pythagoras.
You absolutely would use Pythagoras theorem. Let's see if you guys remember your Pythagoras theorem. Does anyone remember how to deal with a problem like this? How do we deal with a problem of a triangle like that? How? A squared plus B squared equals C squared. Does it matter which one's A, B, or C? One of them matters. Which one is C? That's right, the hypotenuse. How do I identify the hypotenuse? It's the slanted one. Right? Is it the longest side? Yeah, that's another way to think of it. It's the one across from the 90-degree angle. So I can fill in a 5 there, right? Because we know it's 5. A doesn't matter. Let's just leave that as A squared. We know what B is. B can be 4, right? So let's make that 4 squared. Now this is just algebra. Why don't I get rid of the 4 squared by subtracting it from both sides? So I have a squared equals 5 squared minus 4 squared. And to get rid of the squared, I can take the square root of that. So 5 squared is 25. What's 4 squared? 16. What's 25 minus 16? 9. You were close. You were wrong, but you were close. What's the square root of 9? 3. So here you can see again a practical application of this circle stuff in action.
Are we ever going to use this in real life?
All the time if you find a career that involves any type of measurement, or often this is very much part of construction. If you're not involved in those fields, then probably not, okay? All right, here you can see this is in the notes. It explains everything I just went through. I'm not going to do it again, but it goes in and explains in notes all this stuff, so you can have that in your notes as well, if you so choose. This is not part of the required notes in the examples, okay? So that's all in there. So again, what we covered here today is the first portion of this, up to here. This second portion we'll cover in part 2. So in part 2, we're going to talk about some other stuff like, where is it? Tangents. Anyone heard that word before? Okay. And then how this applies and stuff like that. So, okay. And I'm going to give you guys the rest of the period and time to work on the first assignment. All right.